So 2.6, rational functions and asymptotes. Our main function is going to be looking at end behaviors and limits. I'm kind of assuming that you know how to graph a rational function from Algebra 2, but we're going to be looking at how those end behaviors approach the asymptotes. So before we do that, let's talk about the basic reciprocal function, which is f of x equals 1 over x. We have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. The transformation, if I take the x and I add 2 in the denominator, that's going to be the horizontal transformation, opposite of what you think. So that graph is going to move to the left 2 units. The subtract 1 is the vertical shift, and it's going to move the entire graph down 1 unit, subtract 1. So what I like to do, you guys, is I like to start with the asymptotes. And what I did is I moved this asymptote to the left 2. So I did that first. And then I moved this vertical asymptote down 1. And then once I moved the asymptotes, all I did was sketch in the 2 curves. So that's a really easy, quick way to graph. So let's look at the next one. We're looking at the transformations. We have f of x equals 1 over x. So looking at that, we are going to take that graph and we're going to shift, reflect, and stretch it, and then we will talk about the domain. So to the g of x, the negative up top could be moved out in front, which is actually a reflect over the x-axis. So that negative is going to flip me over the x-axis. The x plus 1 in the denominator is going to shift me horizontally left 1, opposite of what you think. The 3 here is a vertical stretch by 3, and the subtract 2 is going to move my whole function down vertically 2 units. The domain is going to be all real numbers except for where that vertical asymptote is. Well, if you look at here, if I put a negative 1 in, negative 1 plus 1 is 0. So I have to have a vertical asymptote at negative 1. So the domain is going to go from negative infinity. Oh, and it's right here. Domain is all real numbers except for negative 1. So negative infinity to negative 1 and negative 1 to infinity, if you want to write it in interval notation. All right, so looking at the next problem, we have g of x is equal to 4 subtract 3x over x subtract 5. Now that is not ready to shift, reflect, and stretch yet. So what you have to do is divide. Now I used long division here. I could also use synthetic division. So I would put 5 in the box. That's going to be your k. And then this would have to be in order. So it would have to be negative 3 first and then 4 second. So I would bring negative 3 down. Negative 3 times 5 is negative 15, and negative 15 plus 4 is negative 11, which is the remainder. So if this was x to the first, then the answer is going to be negative 3, subtract 11, that's your remainder, over the x minus 5, which is your divisor. All right, so now it's in the correct form. You may be used to seeing it this way, where I take the negative 11 over x subtract 5. I put that out in front, and then I have subtract 3. All right, so let's go ahead, shift, reflect, and stretch. Lots and lots of fun. So looking at this, the negative 3, here's the negative 3, and I don't know why there's a line there, just there is, typo. The negative 3 is going to move that graph down 3. So that is a vertical shift down 3. The 11 in the top is your vertical stretch. So looking at that 11 in the top, you have a vertical stretch. Vertical stretch by 11. The negative out in front, that's going to reflect you. That's like this negative out here in front. That's going to reflect you over the x-axis. So this is reflect over x-axis. And the x subtract 5 is going to shift my graph horizontally opposite of what I think. So if it's subtract 5, it's actually going to go to the right 5. And that's the shift, reflect, and stretch on example 2. So looking at example 3, we're going to be investigating end behaviors. So you guys are familiar with this notation. We have the limit as x approaches a of f of x. And that means we're looking at the limit from the left side and the right side. But when we have the limit as x approaches a with a little negative, that means a from the left-hand side. And if I have the limit as x approaches a with a plus, that means a from the right-hand side. So let me just give you an example of what that means. So if here is your graph. Ooh, that's really crooked. Let's try one more time. Ooh, not so much better, but okay. So say there's my graph, and let's just say that I have this asymptote. So here's my asymptote, and I'm going to call my asymptote A, all right? So how this works is the limit as x approaches A, and if you have a little minus, then that would mean from the left-hand side. So that means that I am coming in to A from this left-hand side, all right? So that's the left-hand side. If I want to come into A from the right-hand side, it would be the limit as x approaches A, and then you would put a plus. So over here is the right-hand side, and let me put that one, oh, I don't know. Should we do it in black? And so now I'm coming in to A from the right-hand side, all right? So the plus is from the right-hand side into A, and then the minus, maybe if I have that in pink or red, the minus means you're coming in from the left-hand side. So this would be the left side, and this would be the right side. All right, so looking at this, I would say try example 3 on your own and then check it with the video. All right, so looking at here I have a asymptote here and I have an asymptote there. So let's start with the limit as x approaches 1 from the left-hand side. So what that means then is here's 1 and I'm coming into 1 from the left-hand side, so from over here. And as x gets closer and closer and closer to 1, where does y go? Well, as I'm moving in from the left side, closer and closer to 1, y is moving down, 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 down to negative infinity. So your answer would be negative infinity. The limit as x approaches 1 from the right-hand side. So now I'm coming in from the right-hand side, and as x is getting closer and closer and closer to 1, where is y going? And if you look at it, y is going all the way up here to infinity from that right-hand side. So this would be infinity. All right, the limit as x approaches negative infinity. That means we're looking here. As that goes left, 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 left forever, where is it getting closer to as far as y goes? Well, it's getting closer and closer and closer to that asymptote of 2. The limit as x approaches infinity. So here, positive infinity means as I'm going right forever, what am I getting closer and closer to? And I am getting closer and closer and closer to 2. Now you guys notice that 2 happens to be my horizontal asymptote. So these ends are approaching the horizontal asymptote. Very, very interesting. So because graphs approach asymptotes, we can predict end behaviors. So ends are what are happening to the ends of the graph. We can predict those by looking at the asymptotes. So let's talk about asymptotes. There are two types of asymptotes. We're going to talk about a horizontal asymptote and a vertical asymptote first. So a horizontal asymptote, ooh, that did not work. A horizontal asymptote is an asymptote that goes across like this, all right? Now, we have different, we can predict where that horizontal asymptote is based on the equation. So if we have a rational function, so here's the rational function, and let me just give you an idea of one. So y equals, we're going to do x over x squared plus 1. All right, so there's a rational function. And the rational function, if you look at the degree in the numerator, the degree in the numerator is a 1. And the degree is the highest exponent on a variable. The degree in the denominator is a 2. So that means that the bottom has a larger degree than the top. Anytime the bottom has a larger degree than the top, the horizontal asymptote will always be y equals 0. Now, how I remember this is I picture, so you guys, here's a graph. Here is a y equals 0. I picture a person sitting on that axis. So bottom heavy, your bottom is on the axis, which that axis is y equals 0. I know it's kind of a weird way to remember it, but that's how I always remember that that horizontal asymptote is going to be y equals 0 when the degree in the bottom is larger than the degree in the top. Okay, same-co. So same-co rhymes with Costco. So same-co is how I remember the next one. And what same-co means is it means when you have a rational function, the degree in the top, so this would be like x to the third, is the exact same as the degree in the bottom. So 3x to the third plus 5. So you can see that the top has a degree of 3 and the bottom has a degree of 3. And so because the degree is the same in the top as the bottom, we know that it's going to be the same, all right? Same degree. So what does the co stand for? That means that the horizontal asymptote, which is always a y equals line, is going to be the coefficient, which is 1 over 3. All right, so far we've been looking at horizontal asymptotes. So these are horizontal lines where the graph will approach. It's always a y equals equation. If the graph is bottom heavy, meaning the degree in the bottom is greater than the degree in the top, your equation or your asymptote is at y equals 0. If it's same co, it means the degree in the bottom is the same as the degree in the top. Then you get the coefficients of those degrees. So 1 over 3 is y equals 1/3. Top heavy. So top heavy is when the degree in the top is greater than the degree in the bottom. So you would have something like y equals, and maybe you've got 2x to the fourth over 3x cubed plus 1. So we have a rational function again. We've got this fractional function. And if you notice, the degree in the top is a 4 and the degree in the bottom is a 3. So this is called top heavy. On top heavy, the horizontal asymptote is actually none. There is not a horizontal asymptote, none. Now there may be a slant, and that's going to be like a diagonal asymptote. And you get a slant when the numerator's degree is exactly 1 degree more than the denominator. So I gave you an example of where there's no horizontal asymptote, but there is a slant. Now, how do you find vertical asymptotes? Well, vertical asymptotes you cannot cross, and you're completely undefined at vertical asymptotes. That's because the denominator is going to go to 0. So how do you find a vertical asymptote? You simply set the denominator equal to 0, and that's going to be your vertical asymptote. And so you're going to get an asymptote that goes up and down. The equation of the line is going to be x equals something, and that's going to be your vertical asymptote. So let's look at example 4, and let's kind of look at limits, looking at the end behavior. So the first one I think is kind of the hardest to understand, but what we have here is we have an x to the third, so we have a rational function, we have an x to the third, and then here is an x to the first. And so we have actually what's called a top heavy. So we know for top heavies, there is no horizontal asymptote, all right? Because there's no horizontal asymptote, that basically means that your limit is there, you're not going to have a limit. So not only is there no horizontal asymptote, but there's no limit. And so what's going to happen is if you take this top and you divide it by the bottom, your end behavior is going to approach this value. Now you don't worry about the remainder because it's so small, it doesn't really matter. So your end behavior is going to approach this quadratic function, which is basically going to go out to infinity. All right, let's look at the end behavior of the second one, B. So if we take this second one and we take the denominator and we were to multiply out this denominator, we would have 3 times 2x plus 1 times 2x plus 1. And so multiplying that, I get 2x times 2x is 4x squared. Outside insides is plus 4x, and last times last is plus 1. And you would multiply that whole thing by 3. So the denominator here is going to be 12x squared plus 12x plus 1. And if we look at the degree then, the degree in the numerator happens to be a 2. And the degree in the denominator is also 2. And so this is what we call a same co, which means that we're going to look at the coefficient for the horizontal asymptote. So the horizontal asymptote, if the coefficient in the numerator is 6 and the coefficient in the denominator is 12, then the end behavior is going to approach this horizontal asymptote of y equals 6 over 12, which is going to be y equals 1/2. And so if you were to graph this, those ends as you go to infinity or negative infinity are going to get closer and closer and closer to 1/2, the horizontal asymptote. All right, let's look at the next one. So looking at this next one, we have x equals x squared over x cubed plus 2x squared. So what's going to happen here is you can see that the degree is a 2 and the degree is a 3. So I would consider this one bottom heavy. So the equation for the slant is y equals 2x plus, and you could do 1 1/3 if you wanted. You could do 1.3, or you could just write 4/3. And that's your slant asymptote. Last example, we're going to find the horizontal and the vertical asymptotes. So you can see here that we are same Ooh, didn't mean to do that. So we have a square and a square, which is same So the horizontal asymptote is going to be y equals, which makes it go across, and you look at the coefficients. So 6/1 is 6. The vertical asymptote is you simply take x squared subtract 4 and you set it equal to 0. This is a difference of squares. X plus 2, x minus 2 equals 0. Zero product property means that you would put each of these equal to 0. And so x is equal to -2 and x is equal to +2. So the vertical asymptotes are x equals -2 and x equals 2. The horizontal asymptotes are y equals 0. So coming up, we will be focusing on limits and what happens with those end behaviors as they approach vertical asymptotes and approach horizontal asymptotes. For reflection, you can put whatever you want, and that is everything.